Okay, so I said devise a way, without using the principle of area, to estimate the insect population at t equals 1 month. Suppose the population begins at 105 bugs. Represent your solution computationally and graphically and find the estimate. Okay, so I kind of left this open-ended. See what you guys would do. But the first thing is, let's practice here interpreting points. So we've got this graph. What is a graph? A graph is not just a wavy line, okay? It's not a wavy line. What is it? What does a graph consist of? I know Adam knows. Does anybody else know what a graph consists of? It's not just a wavy line. What is it?
A function.
Okay, it's representing a function, but what does it consist of? What are you looking at when you look at that curve?
Points.
Points. Who's that? Points. You're looking at points. You're looking at how many points? 1, 2, 3, 4 points. You're looking at 4 points there?
Yeah.
How many points are you looking at when you look at that curve? Infinite number of points. When you see a graph, that's what it is. It's an infinite number of points. So making sense of a graph means making sense of what it's made up of. It's points. Okay? So here, like this point right here. What does it mean? So that just isolating that one point on the graph. What do we mean by that one point? Well, we mean its coordinates. What are its coordinates? 1.2. And it looks like it's right on this one, right? Yes, 35. 35. What does it mean? So what does the point mean? We got this ordered pair 1.235. What does that ordered pair 1.235, which is ordered pair for that point, what does it mean? So we did this at the end of class yesterday. In order to understand what this graph is showing you, you have to be able to pick one point and be able to very clearly articulate what that means. Okay, so in the context, right? So what are our units here? This is months. And what are our units on the y-axis? Bugs? Number of bugs?
No, right now.
Okay, number of bugs. What? Per month. Okay, so now you have all the setup information. So we're going to get with our partner here and take 30 seconds to a minute, and you're going to explain. What does this one point mean? I want to know, what does that point mean in the context? Relative to the insects. What does that point mean? Go. What does that point mean? Get a partner and talk. Everyone talk it out.
So once at a rate of 35.
Okay, let's hear what you talked about. So how about back here, the hat? What does this point mean on the graph? Can you explain what that point means?
It's the rate of increase of bugs at the month 1.2.
So at the month 1.2.
Yeah, the rate is 35.
At 1.2 months after the beginning of this experiment, or what's going on, whatever's happening here. What's that?
The rate of bugs increasing is 35.
The rate that bugs are increasing is 35 bugs per month.
No.
Oh no, go ahead.
It's, the rate of population is increased by 35.
The rate is increased by 35.
Yeah.
What do we think? So is it 30? Is it increasing by 35 bugs per month, or is the rate increasing by 35? The rate is increasing. What is the number 35? Is it a rate of change of the rate, or is it the rate? It's just the rate. It's just the rate. This is the rate of change. It's not the rate of change of the rate. It's just the rate. Okay? So you were going like the rate, you were going how fast the rate was changing. So no, 35 is just how fast the bug population is increasing at that moment. Okay? And then the population starts going down here, right? Population starts decreasing. Right?
No. The rate of change is decreasing.
Okay, so what is right here at 1.4? What's happening to the population at 1.4 months? Increasing because the rate of change is positive. It's still positive. So in these first 1.7 months, when is the population the greatest? In the first 1.7 months? In 1.7 months. Why? Because the population is increasing the whole time. This is a positive rate of change. Okay? Okay, so I guess we got that down. That was a struggle at the end yesterday, but it sounds like we corrected that. Okay, so that's just interpreting points. Now, so in this exercise, it says we want to figure out how many bugs there at 1 month, how many bugs have accumulated, right? What's the total amount of bugs? And I think you had an earlier exercise. Was the earlier exercise about the first 0.2 months?
Yes.
Okay, the first 0.2 months. So it gave you 3 possibilities: 20 bugs per month, 45 bugs per month, or 60 bugs per month. Is that right? Which one of those is relevant for us here? 20, 45, or 60 bugs per month? In terms of, we're going to think about really making an estimate for what's happening in the first 0.2 months. Which rate would be relevant? 45, right? 20 is obviously too low. The rate starts at 30 and maybe peaks at 60 or close to 60. So saying that the rate is 20 for that whole 0.2 months is way too low. Saying that the rate is 45 seems like a reasonable estimate if we needed a constant rate, right? 60 then is too high, right? 60 is too high. So you found that so that rate of change was 45 bugs per month. And if we want to know then approximately how many bugs the population grew by in the first 0.2 months, what do we do? Yeah, so if it's 45 bugs per month, then we're going to take 0.2 of that. So at 0.2 months, it's going to be 0.2 of 45 bugs. And what is that? 9. Exact or estimate? Exact or estimate, given this changing rate function? That's an estimate of how many bugs, right? That's an estimate of how many bugs in the first 0.2 hours. Okay? And we said that this principle was, we called this K, right? And we called this is our change in X. And K delta X equals delta Y. And we said this is the way we can symbolize or kind of put notation on this idea that if you have a constant rate of change, you take your rate times your change in your independent variable, gives you that amount of change of the dependent variable. In this case, the dependent variable is number of insects, the number of bugs. Okay, and so if we wanted to keep going like that, we could look at the next 0.2, and we could kind of estimate. So it starts pretty high up here, near 60. At 0.4, it's about 30. So what's a decent estimate? From 60 to 30. So we could just say halfway between those, right? Halfway between 60 and 30 is 45 again. So we could, for that, we could just do 45 again. I'll just put a little mark. Okay, and then from 0.4 to 0.6, it goes from 30 to about 15. What's halfway between them? 22.5, right? Something like this. And then from 0.6 to 0.8, 20, that's fine. Or maybe something lower than that, maybe 15. And then from 0.8 to 0.1. So this is an exact science. You could all have something different. Every one of you could have a different approach or different constant rates, and it wouldn't that they all could be correct because we're making an estimate. And then from 0.8 to 1, right here maybe at 20. Are we making rectangles? No, we're not making rectangles. We're making a pretend rate function. A pretend rate function is we're trying to mimic that existing rate function with constant rates. And that pretend rate function has nothing to do with vertical lines, right? Or rectangles. We're trying to reproduce this blue curve with a bunch of constant rates because we can use this if we have constant rates. We can use this very simple tool. And then what are we going to do? We're going to go k1 delta x plus k2 delta x plus k3 delta x plus k4 delta x plus k5 delta x. One, two, three, four, five. So we got our 5 different rates. We got our change for each one. And so we're summing up the amount of change for each 0.2 month interval to get this total estimate of the number of bugs in the first month. Okay? And so because these all look alike, they all look alike, they're all k delta x. The only difference is which k we're picking, right? So we have a shorthand way of writing a sum. And what is that? You guys know this? This is not a scary symbol to just make you not like math, right? This is to make it easier. This is like, so we don't have to write all those over and over and over again. We just say, okay, we're going to sum a bunch of things up, and they all look the same. So we could say like k sub I delta x. We're going to sum up a bunch of these, and I is going to start at 1, and it's going to end at 5. So we're going to sum up the change in the first interval plus the same change in the second interval. So this, what I just wrote here, is exactly the same as what we wrote up here. Sum up all the changes in the number of bugs to get a total estimate of the number of the increase in bugs in the first 1 month. So what is this? This is Greek sigma, right? Greek sigma. Sum. And then you can do the math, right? So you've picked off your different values for k's, and you just k times 0.2 plus k times 0.2 plus k times 0.2, and you get that estimate. And every one of those was positive, right? Even through here. Bug population is doing what? Even through here. Increasing. Got a positive rate of change, right? Okay, any questions on that? Okay, so this is the idea of it that we're trying to mimic. So there are other ways that are kind of more systematic, rather than just kind of looking at the graph and saying, oh, the average rate through there is this one. And that's kind of what we've been doing so far. But there are other ways to create this that are more systematic and still do the job. So for instance, we could say, let's look at every interval, and we're going to take the exact rate of change based on the blue curve at the left side of every interval to be the constant rate for that interval. Does it make sense? So if I'm doing that first interval, and I'm going to use the actual rate at the left side of the first interval, what rate am I going to have for that first interval? What is the true rate of change at 0 months? 30. So if I'm looking at the left side of the interval, the true rate of change is 30. I'm going to say, okay, I'm just going to make that the rate for the whole interval. And then I'm going to look at the second interval. and I want the true rate of change at the left side of this interval. What would you estimate that to be? Well, I gave you the point right there, right? So whatever this value is, 56, and I'm going to use that to be the true rate of change for the whole interval. For point 4, it looks pretty close to 30 again. I'm sorry, for the third interval from point 4 to point 6, we're going to use the actual rate at the left side of the interval and make that the constant rate for the whole interval. And then point 6, about 15. So from point 6 to point 8, I'm going to use that constant rate of what it was at the beginning, and then at point 8, use this one. So this is another system for making that pretend rate function. I'm basing each constant rate on the true rate, the actual rate at the left side of the interval. That should also be familiar from Calc 1. Is that kind of a familiar idea? Okay. So then I could use the right side. I could use the midpoint. So it's just that we have different ways of systematically creating this pretend rate function. So this is like the left side approach, right? Okay, so then we could do the same thing again. We could take these 5 rates, multiply each one by our delta x, add them all up, get a new estimate for the total increase in bug population for the first month. So in your homework, you're going to do some more of these, and it's going to tell you, use the actual rate at the left side, use the actual rate at the right side. Okay, and so you just got to follow the instructions carefully. Okay, any questions on the homework? So again, our estimate amount of change, estimated total change is the sum. In this case, we got 5 intervals of 1 to 5, k sub I delta x. And that's just k delta x plus k delta x plus k delta x plus k delta x plus k delta x. That's just it's a shorter way to write that. Capital Greek sigma means sum. So let's go back and look at that flag lowering example that we had from yesterday. And question.
Does it need to be equals 0, not 1? Down there.
No, we want to do 1 because this is the first interval. This is the first interval. It's our first rate. So we want that to be the interval number. So that it's, you know what I mean?
Yeah, but it's the left side, so it should be 0. That's what I learned in Calc 1.
No, it's not an x value. So this I is not an x value.
Oh.
You could do it either way. Okay, so you could do from 0 to 4 or 1 to 5. But I think it makes the most sense for I, this index, to stand for which interval it is. So there is no 0th interval. You would always start with the first interval.
Okay.
Yeah. But yeah, it can be, it's what's called shifting the index. You can shift the index and you can make it I equals 0 to 4. But it ends up being the same calculation. Okay. Other questions? Okay, so let's go back to the remember the flag lowering. Okay, so we had the unrealistic. What was the unrealistic? This was the unrealistic version of the flag lowering, right? The soldier is pulling down, but he's able to maintain this exact steady rate of negative 0.75 meters per second. And we said really, that's unrealistic. When you look at the rate of change of some object, usually it's a changing rate. So we said this is more realistic, right? That when he's actually pulling with his hands, it's the negative 0.75. But in between, what happens? The flag does what? When he's changing hands. It slows down for a split second, and then when he grabs with the next hand and pulls with the next hand, then it's at that negative 0.75. So we said this is more realistic, but it makes our task a lot harder. Why? Because now we have to do what we did. We have to break it up into intervals and look at the individual, like try to mimic. So let's look at mimicking the. So here is 0.3. Let's turn this on here. Okay, so can you see the gray one? No. Let's try like the. Does that show up? That's better. Okay, good. All right, so you can see the actual graph. And now here's using intervals of 0.3 using the left sides. Okay, we talked about this. Using the left sides. How about this? How are we doing at pretending to be the rate function? Let me just turn it off. So you know what that actual rate function looks like? I'll turn the actual off. How are we doing here at the actual, so try mimicking the actual function with these constant rates? Good or bad? Bad, right? So let's like, you can barely see what the original rate function looks like when you choose 0.3 and choose the left sides of each interval to be your constant rate. Okay, so then we talked about how can we make the approximation better?
Smaller intervals. Okay,
smaller intervals. And what does that do? Why does that make our estimate better in terms of amount that the flag has come down in a certain amount of time? Why does a smaller interval improve our estimate? You remember what we said? Why is this a bad estimate? The picture tells 1,000 words. So why is the estimate bad here?
We'll have more values.
What's that?
We will have more values.
Have more values. Okay.
It misses a lot of like the velocity changes when you have such long.
Yeah. So what we just said is does this pretend rate function reproduce the actual rate function very well? No, it's terrible, and therefore we get a bad estimate. So what happens when we make the interval smaller? What happens to our pretend rate function when we make the interval smaller?
More accurate.
Okay, so yeah, so let's watch. So that's 0.182 for delta x. But it's still pretty ugly. So okay, here's about 0.01 for delta x. Getting better? A little bit, not much, a little bit. At least now we can see where he's pulling. You see that you're reproducing that negative 0.75 pretty well, but we're not doing very good on the rest. Okay, so here is 0.0227. How about now? So you have to remember, this is a bunch of constant rates. A bunch of constant rates such that delta x is 0.0227. Okay, here's delta x of 0.005. Are you able to see the curve parts? Yeah, so what happens when delta x gets really, really small? What happens to our pretend rate function with all constant rates?
It's become function.
Does a really good job of mimicking pretending to be the actual rate function, and therefore an estimate based on that pretend rate function, an estimate for how far the flag falls. Good or bad? Good, right? Good. Okay, so that's the next principle. And so then if we wanted to get an exact estimate, well, we could make delta x super, super small, like 0.000000001. We make delta x super small, then it's like indistinguishable from being an estimate to the exact amount. So let's summarize that. So what are we doing here? This everything we're doing yesterday and today is about making sense of this, the fundamental theorem of calculus. Okay, so we're going to try to tie it all together today. And what was principle number 1? So what is this for? This is for calculating an amount or an amount of change. That's what this equation does. It calculates an amount or an amount of change. And since we're going to be spending so much of this course doing integrals, what you see on the left, or creating integrals, investigating them, and solving them, we better know what's going on here. Okay? So we want to calculate, this is for calculating an amount or an amount of change. And principle number 1 was constant rate of change. Delta y equals k delta x. And this is just the idea of if you're going 70 miles per hour on the highway and you've got your cruise control set at 70 and you go an additional half an hour, we know that you will travel how far?
55.
35 miles. This is just a general formal way to represent this kind of thing. If you're going 70 miles per hour on the highway and you go for an additional half an hour, that's your change in time, then your change in distance traveled will be 35. 70 times 0.5. Okay? Or if gas is $3.10 a gallon, and you put 10 gallons in you put 10 more gallons in your tank, so you're going to put additional 10 gallons in your tank, and gas costs $3.10 a gallon. What does that tell us?
$31.
You're going to pay $31 for that. You're going to pay an additional $31 for that. The change in price will be 31. So it's this delta y equals k delta x is just representing a very simple idea of the meaning of constant rate of change. Okay, principle number 2. We said that really, though, if you're looking at the rate of change of some object or some quantity, usually it's a changing rate, right? Realistic rates are usually changing rates. And so here's the picture of the flag lowering again. That's principle number 2. Principle number 3 is build a pretend rate function, right? So we want to mimic the rate function with constant rates so we can apply principle 1 and then add up the changes to estimate the total amount of change. Right? So we like principle 1. It's super easy, but it doesn't work for a changing rate. It only works for a constant rate. So we can take this changing rate and chop it up and use constant rates to mimic it, and then add up all the changes using k delta x plus k delta x plus k delta x. Okay, so then we said the total change is the sum of the k delta x's. Are we good? Next, can I go to the next slide? Okay, principle 4. Make more smaller intervals. Right? We said if your intervals are large, it's not making a good rate function, you're not getting a good estimate. So we make more smaller intervals. Okay? Better pretend rate function, better estimate of total amount. Better ingredients, better pizza. Right? Same thing. If you get a better pretend rate function, which comes from more smaller intervals, you get a better estimate of the total amount. And that's what I just showed you, right? So principle 5. All right, well, let's just keep going. Make them super small intervals. That will give us an exact amount. or exact amount of change. Okay, and how are we calculating that amount of change? We are doing sum of k delta x. And so here's what happens. When you make those intervals super small, if delta x becomes super small, then we have a new way of writing this. How do we write this? What's the new way of writing this sigma k delta x when delta x is super, super small? No, we don't want 0 because then that's 0, right? We're multiplying by lots and lots of small rates by very small intervals. So it's not 0, but what does this, does anyone know what does this become when delta x is very small? Yeah.
Doesn't it become a limit as it approaches 0?
Okay. And then what? So yeah, so we're talking about this principle 5 is like a limiting principle, that's right. But so then what notation do we have? Yeah.
Did integral?
That's integral. That's what integral is. That's what integral is. It means sum of a bunch of super small changes. So notice the parallels here. Greek capital sigma means sum. This is German S. It also means sum. Okay? It means sum. So those are the same. What else is the same? What else do you see that's the same here? Delta x. So we said now delta x is super small, so we have a different way of writing that, which is dx. Right? Dx. So delta x, when it's super small, is dx. And what else?
Function.
The function. Okay, so what is the function? What kind of function is it? Rate of change. And that's what we have there, k, right? So here's our rate of change, k, for each interval. Well, now when delta x becomes super small, it's like we have this continuous stream of rates, right? Imagine delta x being super, super small. So as soon as you move a little bit, you have the next rate. Well, that's exactly the idea of the rate function, right? As soon as x increases, you get the new rate according to the rate function. So then we got the discrete k's, the constant k's, become the continuous rates that we get as the outputs of that function. So whenever you were doing a problem, right here. So you do, at the end of the course in 266, you did problems like this. You know. Did you solve problems like that? Things like this? So, did you know what you were looking at? What is that right there? What kind of function? It's a rate of change function. The things they don't tell you, right? The things they don't tell you. When you're doing an integral, it's a rate of change function. And we're multiplying what? A rate times a little change in x. And then we're increasing x a little bit and taking the next rate times a little change in x. And so we're summing up all these k delta x's, but this is super small now. There's like a zillion of them, right? So it's still the sum of k delta x. It's just that sum is like a zillion terms long. And so we represent that that's the integral. The sum of a bunch of bits of change. Okay, so that takes care of the left side. So the first 5 principles are about understanding what the left side is. Summing up bits of change using rate of change. Summing up bits of change using the rate of change. Okay, so then the last principle is tying it to the other side. Okay, so let's look at that. Let's go back to the flag example, and we'll tie it to the other side here. Any questions? Hopefully now, when we're looking at integrals, we've got some meaning behind it, right? And so then what's the a and the b? That's the only thing we haven't talked about yet. So the a and the b are what? Okay, well, but in terms of calculating an amount of change, what are A and B relative to? We're going to calculate an amount of change.
Number of intervals.
Number of intervals?
Is that right?
No.
It's like the domain.
So your domain. Okay, so they x values or y values? They're x values. So this is where we're going to start calculating the change in y. And this is where we're going to end. So this is x equals a, and this is x equals b. And so it's where it's the starting value of x, where we're going to start looking at how much y is going to change, and then b is where we're going to stop x. And so it's how much does y change between x equals a and x equals b. Okay, so now, that the first 5 principles are about this, about that integral notation there on the left, right? It's loaded, right? So it was a long journey to really make sense of that whole thing. And then and we do it in about a month in Calc 1 when I teach it. But so you just got it in a day and a half, okay? So that's the overview. So let's go back and look at principle 6 here. Go back to the flag lowering problem here. And now I want to show you, so we'll go, so when delta x is super small, like I'm showing here, it's virtually the same as the actual function. So we're assuming that delta x is really, really small, and we've got this exact rate function of the rate of change of the flag, okay? So what about a function that is actually the height of the flag? So here the flag is at its starting point is at 5 meters. Okay, and according to this rate function, we have this function is actually the height of the flag. Okay, so what I want you to do is, I want you to interpret some points. So here's a point. And here's a point. I'm going to practice here. The meanings of points. So you got 4 points. I want you to get with your partner, and you're going to interpret the meaning of each of these 4, this point, this point, this point, and this point. So do your best. If you need to get some numbers, get some numbers. Interpret those 4 points. What do those 4 points mean? Because graph. Okay, here's the structure. Explain the meaning of the point using numbers and talking about the flag. That's what I'm asking you to do. Explain the meaning of the point using numbers, specific numbers, talking about the flag. You're going to do that twice. Once for A, once for B. Okay. Good about that? Okay, it's important, really important exercise, because looking at a graph and understanding it means understanding that it's a bunch of points and knowing that each point has meaning in the situation. Each point has a very specific meaning. Ready to go on? Okay. So let's call this one, so we've been calling the rate function f of x, so we will call it f of x. Okay, and then we'll call this function f of x. And so let's investigate, say, from point 7. So x equals 0.7 to, let's say, x equals 2.2. And then over here, that's from here to here. So I want you to represent, you're not doing any calculating, you're just representing, you're just writing expressions that would represent how much the height of flag, the change in the height of the flag starting at 0.7 seconds to 2.2 seconds. Okay, this is for your notes, this isn't for the sheet. So I want to know, we're all about here figuring out how much some quantity has changed, right? That's our whole goal. How much does the quantity change? So the quantity in focus here is the height of the flag. How much does the height of the flag change starting at x equals 0.7 seconds to x equals 2.2 seconds? Now I'm not asking you for an answer, I'm asking you to write something that represents that. How much the height of the flag changes from x equals 0.7 seconds to x equals 0.2 seconds. Can you write something that mathematically equals that?
0.2 or 2.2?
2.2, sorry, thank you, 2.2. Okay, think about it, work on it. So how much does the height of the flag change starting at 0.7 seconds to 2.2 seconds? Talk about it, work on it. Remember, look at your notes, look at what we talked about earlier.
Yeah.
That won't be exact. So that's the same thing as this, but that's so it's totally different than this. Which graph? There's two graphs. There you go.
Okay, so when you have the integral, you want that to be a small line. Because the position is going to be the integral of the left.
Okay, so we can calculate this amount of change. So my point is we can calculate this amount of change using, if we have the rate. If we have the rate, how can we represent the amount of change? Most of you got it. What? You look at lots of little bits of change, right? K delta x for small changes in x. And what do we do with all those bits of change? Sum it up. Starting at 0.7, 2.2. That's what we talked about that earlier, right? So if you have the rate function and you want the amount of change of the quantity that's changing at that rate, that's an integral. That's what the integral is. Okay? But we can also use this function to calculate that amount of change. And what is this function? What's the output of this function tell us? What does the output of this capital F function tell us? What's that? Just the height of the flag at time x, right? The height of the flag. So if we want the change in height starting at 0.7, ending at 2.2, how can we use this function to do it? Yeah, so we're going to take the final height, f of 2.2, and the initial height, and simply do what? Subtract. So we take the final height and subtract the initial height. Both of these expressions calculate the change in height of the flag in that time period. And since they both calculate the same thing, what can we say about them? They're equal. Okay, and then so how are all right, any questions about that? Does this make sense? What's the relationship between the capital F function and the little f function?
Capital F is the integral of the left.
No, it's not the integral. A function is not an integral. So a function is not an integral. Okay? But so just the relationship of capital F and little f. What is the relationship?
Derivative and antiderivative.
Okay, tell me. So which?
F of x is the derivative of capital F of x.
Right. If little f is the rate of change of big F, which it is, right? It's the rate of change of the height of the flag. Then little f is the derivative of big F. And therefore, capital F is the antiderivative. That's what you meant to say.
Yeah.
Antiderivative of little f. Okay? So capital F is the antiderivative of little f. Why? Because little f is the rate of change of big F. And that's the sixth principle, that you can calculate the total amount of change using the rate function, right? Represent it using the rate function as the sum of a bunch of tiny little changes using the rate and using k delta x, right? K delta x. Or you can calculate that total amount of change just by taking the actual quantity function and taking the final amount of the quantity minus the initial amount of the quantity. And that will give you the change in this case, the height of the flag. And so those two things are equal. And that's principle 6. Principle 6 is there's two ways to calculate the total change in a quantity. As an integral, and just simply as final minus initial of the quantity function. And that completes the fundamental theorem. Can I leave this screen? Are we good on the screen? Everyone got what you need? So I didn't get to that, so we'll just kind of make the slide on the fly, okay? Principle 6. What's principle 6? Two ways to represent and amount of change. Okay, so one is using the rate of change function and an integral. And using quantity function. Final minus initial. And so now that last principle, you're staring at the fundamental theorem, right? Left side is computing the total amount of change using the rate function. What you're thinking is, oh, we're summing up a zillion bits of change, right? K delta x plus k delta x plus k delta x, where delta x is super small. The right side, you're saying, oh, here's the quantity function. Quantity function is If I have a quantity function, I want that amount changed. I just take the final value of the quantity minus the initial value of the quantity. Piece of cake. It's actually principle 7. This quantity function is the antiderivative of the rate function. That's principle 7. And that does it. Anybody have a question? Okay, so let's take a 5-minute break, and then we'll do 20 more minutes. Okay, or 25, I should say. So be back here in 5 minutes. Just be back in 5 minutes. Look at your own watch. Do the math. Don't be late. Okay, be back in 5.
Just this class yesterday.
Okay.
At least the other tutor. I don't know the homework that you have given to students. How am I going to cover it?
If you just send me an email, I can just send you this. Oh, I have an extra one here.
Okay.
Oh, no, I don't. Just I'll just send me an email and I'll send you the sheet and you can do it.
Okay. That's good.
Thanks. Yeah.
I was absent yesterday.
Yeah.
Is it too late if I return the homework tomorrow? Or I can make a scan of it tonight and send it by email.
Well, so if you just missed if you just missed class, why did you miss class?
I was not here.
So now when we look at problems like this, we can think of them in a different way than before. Instead of just, oh, this is telling me to do something, we can look at this and say, oh, this has meaning, right? This has meaning based on what we just worked on in the last couple days. So for instance, this first one, the integral from 1 to 5 x to the 4th dx. So rather than your reaction being, oh, I'm going to do this and this and this, your reaction says, oh, this means something. This has a value. What is the meaning of the value? Okay, so can you describe, this is equal to a number. Can you describe what the meaning of that number is? Can anyone give it a shot? Yeah.
The amount of change.
Amount of change.
From a function from 1 to 5.
Okay, what function? So it's the amount of change of a function as x goes from 1 to 5. And what do we know about that function?
X to the 4th.
What about, it's the amount of the change of the function x to the 4th? What's that?
That function is the derivative. That x to the 4th is the derivative of the function that we're looking for.
Right, so therefore x to the 4th is the rate of change of the function we're calculating the change of, right? So it's the change of some quantity starting at x equals 1 to x equals 5, where that quantity has a rate of change of x to the 4th. So now do you remember how to do it? So we're going to use the fundamental theorem, right? So this integral, we said there's two ways to calculate or show the amount of change. Integral is kind of shows this process of, oh, we're summing up a bunch of little bits using the rate. It's the other side that actually kind of helps us to actually calculate a value, right? So that we can do it. That means we need what? Right, okay, so we need the function, all right? So therefore this equals f of what? 5 minus f of 1, where capital F is the antiderivative of x to the 4th. So the integral expression represents process. It represents what's going on. The right side is kind of our means to compute it. The right side is like, okay, now this is the way we can find that value. So all we need is the antiderivative of x to the fourth. Who knows it? What's the antiderivative of x to the fourth?
1 is 5 over 5.
Yeah, so what function, if you took the derivative of it, would give you x to the fourth, and lots of you got it. It's what? 1 over 5, x to the 5, okay? So now, this notation means exactly the same thing as this. It means plug 5 in, plug 1 in, and subtract. So it's just a compact notation, meaning plug 5 into that antiderivative, plug 1 into that antiderivative, and subtract. So I think we get 625 minus 1/5. Five to the fifth over 5 is just 5 to the fourth, right? And then 1/5, 1 to the fifth. So I did a couple steps there in between. So now 624 and 3/4. 624, say 0.8. 624.8 means what? Is that a rate of change? 624.8, is that a rate of change? Is that a change in x? Okay, I kind of clarified the instruction here. So for each, explain the meaning of the sentence. Then you're going to write out an exact expression for the value. Okay, for instance, 625 minus 1/5. That's exact. And then finally find a decimal approximation. Okay, so you want to get an exact expression using e, using trig functions, whatever. And then at the end find a decimal approximation. Does that make sense? Once you start practicing it, you can do them a lot faster than doing all the steps of u sub. Okay, so I think it's beneficial to do that. So I'm just gonna we're gonna spend time on it tomorrow, so, and also I'll have an introductory sheet in the homework for it. But here's the idea. Okay, so don't. I'm gonna kind of go fast. I just want to show it once in class here. So if you don't get everything, don't worry about it. But the idea is that this is the result of what derivative rule?
Chain rule?
Is it the result of product rule or chain rule? Chain rule, okay. Chain rule says that if we have a function like this, f of g of x and g of f. Chain rule says if you have g of f of x, the derivative is what? The derivative of the outside, leaving the inside the same, and then times the derivative of the inside, right? So we're looking at this problem like it's this, and we're going to try to recover the original function, g of f of x. So if we're looking at this and trying to recover the original function, are we going to focus on here, number 1, or focus on number 2? Which one of these looks like what we're trying to get? First one, for sure, right? So if we can just figure out which is this part, then what are we going to do? We're just going to do the antiderivative of the outside function. And we got it. Do you see that? So if our whole rate of change function looks like this, and we want the original function, the antiderivative, then we just need to figure out which is this part, and do the antiderivative of the outside, leaving the inside the same, and we pretty much got it. So which one of these two things is g prime f of x? Is it 2x or this square root thing? Square root. And what is g prime and what is f? G prime is square root, right? And the f is the x squared plus 3. So what's the antiderivative of square root? 3 over 2, right? Power 3 over 2. And what are we going to do with the inside? Leave it the same. So we're going to take x squared plus 3 and take it to the power of 3 over 2. And then we'll call this the first attempt. Why? Because it's just something that might be close. We might have to do a little cleaning up. So that's our first attempt at this. And then how can we check the first attempt? What can we do to check it? Take the derivative and compare it to what we started with. All right, so we're going to take the derivative. We're going to get 3/2 x squared plus 3 to the 1/2 times what? 2x. And now we're going to compare that to our original rate function. Are they the same? No, they're off by what?
We need to remove the 3/2.
The 3/2 is the problem. Everything looks good except in our original attempt, its derivative has a 3/2. So now, how are we going to adjust the first attempt? What are we going to do to that first attempt? So that when we take the derivative, the 3/2 won't be there.
So I put the
So like 2/3.
2/3, right? So now if my second attempt, I'm just going to take 2/3 of this. That's my second attempt. So that's the first attempt. Second attempt is going to be 2/3 of x squared plus 3 to the 3/2. That's going to be the second attempt. How can I check the second attempt? Take the derivative. Derivative is 2/3 times 3/2 x squared plus 3 to the 3/2 times 2x, which equals, did I blow something there? 1/2, thank you. Equals x squared, so 2/3 times 3/2 is gone, x squared plus 3 to the 1/2 times 2x. Is it the same as what we started with?
Yes.
So, I got it. And then when you get good enough, you can do this, you can add this, include this part in the first attempt. All right, but when we first start doing it, we're going to, just be real simple about it. And the great thing about this is you don't have to get it perfect. The whole point is you don't have to get it perfect on the first try. Just try something you think is close based on undoing the chain rule, right? And then take the derivative and compare it. And if it's not right, then try again. Right? So just don't be afraid to try something. It doesn't have to be perfect the first time. Okay, so I just wanted to expose you to that today, and I don't expect you to be a master right now, okay? But we'll do more of that